Um, okay, so first of all, thank you, G-Bay, who's disappeared, I think, for inviting me. All of my family and work colleagues are convinced this is not a work trip, but it's holiday. And I'm sort of minded to agree with them, actually. I thought before I start, I just wanted to say some words of background. So first of all, I kind of liked going to summer schools when I was a student, not just for the science, but just to meet people, to see people's different approaches to science, and frankly to just steal the bits I liked and not the bits I didn't like. And so I thought I'd start with some background of how I got into oceanography. I did my first degree at Imperial College in physics. Actually, I'll say before that, I had an offer to go to Cambridge to do natural sciences, and I felt I didn't fit there as someone coming from a state school. And actually, that's something that's really affected me in recent years, and I've been trying to remedy, do a lot of work on access. So I was at Imperial College for 3 years doing a physics degree, then moved to Southampton to do a PhD on quantum chromodynamics. I knew the moment I'd arrived I'd made the wrong choice. So I quit my first PhD on the Wednesday morning, having lined up a new PhD back at Imperial. I thought atmospheric physics, but it turned out to be oceanography. So sometimes you have the best plans, but a bit of random event comes along and this was one of those moments. Some people say I had a reckless streak because I did the same as an undergrad, but I then had a stroke of luck. I was working with John Marshall, no relation to me, and John got offered a faculty position at MIT. So we all moved over to MIT as a group, and I was sort of honorary MIT Woods Hole student there. That's where I met Sarah. We were on the 15th floor of the Green Building, amazing views of Boston. It's a very interesting, I would say, strange place, actually, MIT. Then I was still a student in London, so I went back to defend, and that was weird because there was no one there. And then stayed on as a postdoc because I'd only just really arrived at MIT. And then applied for endless jobs and kept being runner-up, which wasn't very helpful with 3 months left on my postdoc. But then the final job I applied for was at the University of Reading. It was a faculty position. I was so out of my depth at the time, but somehow landed that job, and it was a wonderful place to work. I was there for 12 and a half years. And then in 2007, moved to my current role at the University of Oxford. I really wanted to get back to physics again. And part of me, I think, also was thinking, actually, I do have a right to be in a place like Oxford. And actually, I must say, I found it very down to earth and welcoming. So I think a lot of that is just mental, actually, in my head. But I also strongly believe that work-life balance is important. If we really want this to be a career for diverse people, then we need to make it a job, not something where we expect people to work 80 hours a week. So when I'm not doing science, you'll find me either riding my Brompton bicycle, and this was the most insane trip I've ever done on it. And I looked it up this morning, and it beats Barcelona in miles from Oxford. So that was yesterday. Or you'll see me playing music at various venues around Oxford, flugelhorn and piano. And that's my big regret, actually, in life, is that I quit that for 25 years. And if you have a passion, please don't give it up. Don't wait until you're in your late 40s, 50s to take it up again. So I think that's important, and it helps your work life as well. Okay. So this is my structure today. We're going to talk about preliminaries to start off. Very brief overview of wind-driven dynamics in a basin. And then we'll move on to talk about how these ideas may or may not apply to the ACC, the circumpolar current. We'll talk very briefly about energetics of overturning circulation and the ACC. A brief introduction to eddies, which will be the main topic tomorrow. And then I couldn't resist putting this title in, What is the Southern Ocean? And then we'll wrap up. So let's start with preliminaries. So I've got some quotes here, and I want to get you participating. So 3 different quotes on ocean models, which I like. So essentially all models are wrong, but some are useful. George Box. The purpose of models is not to fit the data, but to sharpen the questions, Samuel Carmin. And I have yet to see any problem, however complicated, when looked at in the right way, did not become still more complicated. So 1 minute, turn around to your neighbour. I want you to discuss these. What do you think of these quotes? Are they compatible or incompatible? So off we go. Right, okay, so it's a short minute because we're very mindful of 12:30 here. So what does anyone want to volunteer what you came up with? Yep.
So I'm coming from the paleo community, and a lot of people get really entrenched in the proxy data says this, and the model says this, and if they don't agree, then one is wrong. And really, probably both are wrong, but they both give us tools.
Very true. Yeah. Yeah. I agree. Anyone else? Yeah, okay, I agree. Anyone else? So, did anyone struggle with reconciling the number 2 and 3 here? So I think the reason I put this up is to flag that we use the term models in many, many ways. And actually with paleo, you could argue we should be using inverse models to some extent. But I think most people, when they talk about models, if it's not a statistical model, they're probably thinking about either a conceptual model or they're talking about a predictive model. And if you were making a weather forecast or you flew in an aeroplane to get here, you wouldn't want to go in an aeroplane that was tested using one of these simple models. You want the most realistic model, accurate model you can get, even if it's ugly, and it may well be ugly at times, because engineering fixes are very much part of that. But on the other hand, if we're trying to understand what's going on, then simple models is really what you're aiming for. And I would argue that these are not incompatible. This is about building up the vocabulary that allows us to talk about the ocean at a higher level. And I think the first quote is just basically right, to be honest. Sometimes models that fail are really, really useful in telling you what's not going on. Right, given the time, I don't know if I'm going to do this as get you all to talk about it, but I had some thought experiments. So suppose you blow a uniform wind stress over a basin and over a channel. What would happen? And I'm going to guess over the channel everyone can think up the answer here. So what will we get? Get a sonal current, right? What happens in the basin if I blow a uniform wind stress? Yeah, well, we could call it a bath if you like, and you apply a uniform force. And let's make it simple and make it two-dimensional, so forget the vertical dimension. It doesn't matter, actually, Sarah, it doesn't matter if it's rotating or not. Here. Well, actually, the answer here is no, you get nothing. And the reason is, because it's a uniform force, all you'll get is high pressure on this side of the basin, so if you like, the surface of the water will rise up. And you'll get a sonal pressure gradient that will completely annihilate the wind stress. So there's no wind stress curl if you think about vorticity. Now, in contrast, if you have a non-uniform wind stress, then in this basin you would have got two gyres, subtropical, subpolar gyre, whereas in the channel you'll still get a sonal jet. And that's worth bearing in mind. The geometry, as Matt said, is really important for understanding these problems. And I'll leave you to think about this one. What happens if I have a sort of a basin with a sudden channel, like the North Atlantic, I guess, like the Atlantic, sorry, and I blow a non-uniform sonar wind stress, but to the north of the model Drake Passage. What do I get then? Do I get gyres or do I get a circumpolar current? And I'll leave you to think about that one. We'll return to it at the end. Okay, so overview of wind-driven dynamics in a basin. So I'm going to have to go quickly here, but I'm going to try and keep the mathematics to a minimum. In a summer school, you don't have time to go through everything like you would in a lecture course. So really, I'm just trying to give you tasters, and there are plenty of places you can look up the detail, or you can talk to me if you're interested. So I'm going to hazard a guess. Unlike most schools, most people know what I'm going to tell you, but there's always one or two from a different background for which it may be less familiar. So it's good to just go over the sort of basic territory. So we'll start with the surface Ekman layer. So the wind acts on a thin layer at the surface, so tens of meters thick. And if you look at the textbooks, you'll get these elaborate derivations of Ekman spirals. There's not a lot of observational evidence for Ekman spirals, but they are there if you integrate for long enough, over enough measurements. But the basic physics is really simple in the Ekman layer. So the idea is you have a wind stress at the surface, and it's balanced to good approximation by the Coriolis force. So simple as that. So the wind stress is to the right, the Coriolis force to the left, and then that means that in the northern hemisphere, the Ekman transport is to the right of the wind stress. And in fact, you can write down the formulae pretty easily relating these depth-integrated currents to the wind stress. And I want to stress that the answer here does not depend on mixing in the Ekman layer or viscosities or anything else. It's a really robust and remarkable result. And then if these transports are diverging or converging, then by continuity you have to have water upwelling or downwelling out of the Ekman layer. And again, you can write down the formula. It's a couple of lines of algebra. And the Ekman transport is the Ekman upwelling is the curl of the wind divided by the Coriolis parameter, so 2 omega sine of latitude. And it's worth, again, stepping back and thinking, remembering this is remarkable, because given the wind stress, we can predict with a very good degree of accuracy what the vertical motion is, just tens of meters below the Ekman layer. Yes? Yeah. We do. Yeah. And actually, next slide is very relevant to swimmers like Matt this morning, because if you have a strong wind event here, then there will be a lot of upwelling and it will be a lot colder. So the classic application of Ekman theory is to coastal upwelling, also equatorial upwelling, but I figure that's a bit less relevant to this school. So this is a southern hemispheric sample, wind stress along, equatorward wind stress along the coast of South Africa. The Ekman transport's to the left because we're in the southern hemisphere, so offshore, and by continuity you have to have upwelling. And there's about an 8-degree temperature drop because that upwelling is bringing nutrient-rich cold waters to the surface, and in fact is where you find a lot of the biological activity and hence the fisheries too. So my wife is Portuguese. Going swimming in Portugal is a challenging experience given the contrast in temperatures. Galicia is even worse actually, and and the Med can be quite cold if you've had a wind event. Okay, now I would argue that the ultimate coastal upwelling current is the ACC, essentially the Southern Ocean, because over the Southern Ocean what we have is a wind stress that's to the east. The Ekman transport is then equatorward, and by continuity that means that you must have upwelling of water over most of the Southern Ocean. And then the other thing that's special here is you can't, as Matt said, have zonal pressure gradients until you get down to depth where you've got topographic features. And so the return geostrophic flow occurs in the abyss where it's poleward, and then that's balanced by upwelling and downwelling, and it's known as the Deacon cell. And you might be wondering, well, how do I reconcile that with these water mass structures? And we'll return to that question later in this presentation. But basically then the idea is that that upwelling is going to bring the cold water to the surface. It will create a north-south density or buoyancy gradient. And then through the thermal wind relation, which you get by combining hydrostatic and geostrophic balance, you know that the zonal flow increases with height at a rate that's given by the buoyancy gradient, north-south buoyancy gradient. And so you can integrate twice and you'll get a model for the circumpolar transport. So that's the simplest, I would say, our model for WIDERS and ACC. Now, if we go back to a generic northern hemisphere basin, I'm going to be careful to say northern hemisphere. When I was at Reading, we had an Australian postdoc, and she used to delight in interrupting if anyone presented something without saying that, by saying, in the northern hemisphere. And so we all learned to say in the northern hemisphere, otherwise Morwenna would just shout at us. And she's right. So in the northern hemisphere, then the winds will have westerlies or eastward wind stress at mid-latitudes. The opposite at the equator, the trades and the polar westerlies to some extent. And so you have upwelling over the divergence of these transports means you have upwelling into the Ekman layer in the subpolar ocean, downwelling in the subtropical ocean. And this is a map of the global wind-induced upwelling. It's in strange units, but I really like the figure because it's so clear. And you can basically see what I sketched over there and also over the Southern Ocean, this intense upwelling, or widespread, I should say, upwelling. Now, these numbers are small, you know, when we're talking 30, 60 meters a year or so, but it's really important for the circulation. Okay. Now, what's going to happen then is that upwelling or downwelling is going to drive circulation in the flow beneath. So now we go to fast forward to Sverdrup and Sverdrup balance. And Sverdrup balance is, again, a beautifully simple idea. You take geostrophic balance, assume that the Coriolis force balance is pressure gradient forces horizontally, substitute it into continuity because the ocean is nearly incompressible. And a couple of lines of algebra later, you can show that the beta, the gradient in the Coriolis parameter, times the northward velocity is given by F times dW dz. Then we can integrate vertically from the sea floor to the base of the Ekman layer. Notice I put no topography, bathymetry down here, but actually what I really need to do is assume that W is small at depth, and we'll discuss that maybe in a moment, to just the base of the Ekman layer, and you get this remarkable result that the depth integrated meridional velocity is given by the Ekman upwelling velocity. And in fact, if you add the Ekman transport in as well, then you get the original form of Sverdrup balance, where beta times the integral of phi is given by the curl of the wind stress. And this is basically a vorticity balance. It's saying that if you have a source of vorticity from the wind stress curl, then the fluid parcel has to increase its vorticity. So it's like an ice skater. If you stretch, then the ice skater will spin faster. But in the ocean, vorticity is dominated by the Earth's rotation. So the way to spin faster is to head polewards. And that's basically the physics of Sverdrup balance. And so if we go back to our basin, actually Sverdrup did something really cool, which is a nice lesson for theorists here. He didn't know why, but said observations say that the circulation is closed at the western boundaries. And you can always do that as a theoretician, use the observations. So he penciled in the western boundary currents, and then if you join the arrows, you get subtropical and subpolar gyres. And this is the global prediction for the Sverdrup circulation. And it bears a large resemblance to much of the circulation that you see over the global ocean, depth-integrated circulation, except perhaps in the Southern Ocean. So note in particular the super gyre, subtropical gyre that you get in the Southern Hemisphere. Okay, 1905, Stommel, that's not right, 1948. Okay, how did that happen? How many years has that been there, I wonder? Western boundary current. So I normally have a couple of slides on this, but I thought today all I'd do is just give you the solution. So to close the circulation at the western boundary, you need more physics. And what Stommel did was to introduce a linear drag, or bottom friction, if you like. And the idea is if you've got a vorticity sink, then you must remove vorticity somewhere. And that happens at the western boundary. Now, in all honesty, I think there's an easier way to understand why you get western boundary currents, because in the, well, let's do the subpolar ocean. So in the subpolar ocean, the wind is putting in positive vorticity, anti-clockwise, if you like, vorticity spin. And we know that Sverdrup balance says the flow is polewards. And those two statements coupled together, because the flow must be then counterclockwise if the wind is forcing it in that direction, is enough to tell you that the boundary current must be on the west rather than the east. Okay, and you can write down the vorticity budgets. This is a stream function now for the depth integrated flow. If you're so interested, we will share the slides after, I'm sure. I will correct the year of Stommel. Okay, so enough of basins. Let's get on to the Southern Ocean. So simple models of the circumpolar current, and I'm going to focus in particular on trying to understand what sets the transport of the circumpolar current. And I'm going to take a sort of semi-historical view, trip through this story. So here's the circumpolar current. Matt had a similar, possibly the same picture, I'm not sure. So the circumpolar Fonnian transport consists, I like to think of it as two parts. So the thermal wind relative to the sea floor. So this is the transport minus the bottom flow. And that's pretty well pinned down through Drake Passage. So 137 plus or minus 7 standard deviation Sverdrups. And a Sverdrup, if you don't already know, is 1 million cubic meters a second. And then a bottom flow is, well, there's a paper by, nice paper by Peña and Molino et al. That says it's about 25%. My view is there's a huge error bar on that. So I think I wouldn't bet a lot of money on that 25%. But and the problem is basically a tiny velocity multiplied by 4 kilometers of water by the width of the Southern Ocean. It gives you a huge transport. Okay, so that's what we want to explain. And the first idea, Stommel is my favorite dynamical oceanographer, bar none. He did some great contributions. And this is probably one of his less successful models, but I'll talk more about that in a moment. So it's at the end of a paper in 1957, and he'd published his Western Boundary Current paper on the Gulf Stream, 9 years earlier. So this is a survey of ocean current circulation theory, I think, or something like that. And so what he did was said, well, Sverdrup balance tells us that the flow is moving polewards. So suppose we draw a line that sort of hugs the southern tip of South America, or the northern edge of the Drake Passage. Then we can work out the Sverdrup balance, poleward flow, across that line. Then he said, well, let's assume that that Sverdrup transport equals the Drake Passage transport. And I'm going to ask the question, why would you want to do that? Do you think that's a reasonable thing to do? It's actually wrong, I think. There's no reason here. You can add any zonal flow you like on top of this picture. So the way Stommel drew it is quite clever, because he makes sure that there's a little bit of land, just at that region. But there's no reason why these two have to be equal. And I think it's just a fluke, which is probably a little unfortunate, that Sverdrup balance gives you roughly the right answer for the transport, albeit with a big error bar. Now, actually, Stommel was fully aware of these limitations, and if you go back and read the paper, he actually ends by saying, I'd like to apologize for ending this survey with such a sketchy and incomplete interpretation of the ACC as I've given here. I should have hesitated to do so were it not for the fact that it so clearly illustrates both the usefulness and weakness of the physical ideas. It's another example where just because a model's wrong doesn't mean it's not useful. And Stommel was absolutely aware of these limitations. Okay, so if we move on, then actually one of my favorite papers, but not the easiest read, is by Adrian Gill in '68. So he solved in a homogeneous model, so this means uniform density, 2D flow, no stratification, no bathymetry, and linear drag. So basically Stommel, gyre, but with a reentrant channel. And I won't go through the details, it's quite hard to read these panels, but I've put the transports in Sverdrups. All you really need to know here is that the transports are huge. So the ACC Phonium transport in his model is controlled by bottom friction, and it's crazy large. It probably is even larger if you put a sensible number in there. And then we fast forward 4 more years, so it's not the same paper Matt showed, but it's a similar idea. This is from Kurt Bryan, so it's a homogeneous model again, no stratification. Without bathymetry, but realistic geometry. And he got an ACC that's more than 600 Sverdrups, so at least 4 or 5 times stronger than it should be. 3 or 4. And, but when you add bathymetry, that goes right down to 32 Sverdrups. And again, unrealistic. And you can see the flow now is overly steered by the bathymetry. And that's because, in reality, the flows are much weaker at depth. So a homogeneous model will always overstate the importance of bathymetry. So I take away from this, I don't know if you can read the bottom lines are quite hard to see, I think, from the back. But the conclusion I take away is you need both stratification and bathymetry if you want to understand the ACC. Okay. So can I just pause? Am I going too fast here? I seem surprisingly well advanced on these slides. I'm surprised myself. I'm making an effort to keep moving. So I want to go back to the sonal momentum balance and a really important paper by Walter Monk and Palmer in 1951, which was, I think, years ahead of its time. The first idea is wind stress is balanced by bottom form stress. And I don't know about you, when I first heard about form stress, I found it quite confusing, and before you get on to eddy form stress, which is more confusing, and that's at the bottom of this slide. So let's just try and understand it, because it's a really simple idea. So we started out with that thought experiment of the basin, and I said if you blow a uniform wind, what you do is set up an east-west pressure gradient that annihilates the wind. Well, the same is true in the Southern Ocean too, except the pressure gradients will occur at depth. So basically, in equilibrium, you need a pressure gradient across the Drake Passage or the other ridges, which balances the wind stress. So literally what you're doing here is you've got a pressure gradient force to the right in the land, and it's to the left in the ocean. So you're transferring momentum from the ocean to the solid earth below. And that's all that a form stress is. It's water leaning up, pushing against the land. And this is very well pinned down in models. You'll see almost, to leading order, a really good balance between wind stress and pressure gradient at every latitude. Now the problem is, how do you get the momentum down from the surface to the bottom? And there's basically 2 ways to do this. And one is this eddy form stress. So I want you to focus again, just remind yourself of this picture, and then look at the one below. And what I've done here is to sketch 2 layers, a warm layer and a cold layer, or a buoyant and a dense layer, if you like. And we've got an undulating interface, I can use the beamer here, separating the 2 layers. And for an eddy form stress, it's exactly the same idea, that you then get high and low pressures aligned such that the warm water is pushing against the cold water. And if you think about it, you've got equal and opposite pressure gradient forces then at the same depth, but within the different water masses. And so you decelerate the warm layer and you accelerate the cold layer, and it's equivalent to fluxing momentum from layer 1 to layer 2, so downwards. So just as the ocean can push against the sea floor, so warm layers can push against cold layers, transfer momentum vertically. There is another way to do this, and this is just to have an overturning circulation, which is also a part of the story. So if you have an Ekman cell, then there's a Coriolis force associated with that, which is certainly a contributor too. Okay, so the punchline is that eddies are going to be fundamental to ACC dynamics. Okay, so we've got the ingredients we need now to come up with a more sophisticated model of the ACC transport. And this was really put together in a beautiful paper by Johnson and Bryden in '89, which again was well ahead of its time, I'd argue. Okay, so they assumed that the eddy form stress balances the wind stress. So basically you have a wind stress, the same eddy form stress throughout the column until you hit the bathymetry. They then wrote down an eddy closure that basically relates the eddy form stress to the north-south buoyancy gradients. And I'm glossing over some details here, but you know, they made a particular choice. You can make different choices. These days you might use Gentile-McWilliams in that, but this was before Gentile-McWilliams. And then you simply integrate thermal wind balance, because this basically sets the north-south buoyancy gradient. So that tells you how the flow is increasing with height, and you integrate twice, assuming a level of no motion at the sea floor. So we're not doing the bottom flow component here. And what you will find is that the thermal wind transport varies with the surface wind stress. Depending on your eddy closure, it might be the square root of the wind stress, as in Johnson and Bryden, or something else. And importantly, although it doesn't get stated enough, also the imposed north-south buoyancy gradient at the surface. And so I would argue that leads to what you'll read in most of the textbooks now, which is that the circumpolar volume transport is set by some combination of wind and buoyancy forcing. It's a nice idea. Can anyone think of any issues with this sort of conclusion? Problem is it's wrong. So if you want to know why it's wrong, at least in model world it's wrong, and I will tell you tomorrow why I think it's wrong. I think most of the ingredients here are fine. I think the problem is in this part with the eddy form stress. Matt hinted at the reasons why in his talk, but I'll talk a lot more about this tomorrow. And actually that's another thing I learned from summer schools is never trust what you read in the literature. There are many things that are wrong, and the woollier statements become some combination of wind and buoyancy forcing is a clue. It's often a code for saying we don't really understand what's going on. The other one I keep reading is, because I work on Gulf Stream separation on and off, is that Gulf Stream separation involves a subtle balance of over 20 different processes. That's nonsense. I mean, maybe it's true, but I think it's nonsense. It's just code for saying we don't understand what's going on. Okay, I want to talk about energetics now, and this will lead us to overturning circulation. But this is also a nice theory, actually, for the ACC as well, indirectly. So another classic paper by Monk and Wunsch, so Walter Monk again. We've got a thought experiment. So those of you who live in America don't have kettles, I discovered recently. So maybe this is more use to you. So, and you're not allowed to use your microwave here. If you want to make coffee in the morning, you've got a choice. Do you put your pan on the stove, or do you put it under the grill? Which one is the right answer here? Got to put it on the stove, right? And what happens if you put it under the grill? A long time. Well, why does it take long? Yeah, so we make a diffusive boundary layer here, and it will take a long, long time. I was once in a summer school in Cambridge in their old building where the heaters were I'm not joking, were at the ceiling. And Herbert Huppert used to poke fun at them all the time, and because he said by the end of the day it's just about warmed up and then they turn it off. Now this is the atmosphere, to good approximation. The atmosphere absorbs heat at low levels and emits largely from higher levels, and this is the ocean, heated and cooled at the surface. And it's a very inefficient way of driving a circulation. So what are the energy sources for the ocean circulation? So we have surface heat fluxes, but the problem is we're heating and cooling at the same level. And what does that do to the potential energy? Basically nothing. It's a good job Remy Tallier isn't here. He'd be going ballistic at this point, but he would like what I have to say tomorrow, so he'd forgive me. You have evaporation and precipitation. So there is some difference in sea surface height, across the ocean. So again, this is small, but these, when you do the numbers, these are small terms in the energy budget. So we're going to fade them out. Then we got the wind stress, and then we got mixing. And this is basically tidally driven. So I'm not talking about overflows here, which would not be an energy source, because you're taking it from the mean stratification, but tidal force mixing is important in this budget. And both of these will increase the amount of energy in the ocean. So the winds are putting kinetic energy in directly. The mixing is increasing the potential energy. Okay. And that means the overturning circulation is a mechanically driven heat engine. Now, another of my favorite models is due to Ganadesican, and I think this is basically the same idea, but it's dressed up in terms of the depth of an upper layer. So he calls this the pycnocline depth, the depth at which density, if you like, varies rapidly. Of course, that's an idealization. So basically the depth of the buoyant upper ocean. And we've got the same processes. So basically, buoyancy forcing's represented here through North Atlantic deep water formation, which is taking water out of the surface layer. We got the Ekman transport in the Southern Ocean that's going to drive water in to the surface layer. So, I mean, there's a bit of a subtle thing going on here, because this is in concert with the buoyancy forcing. You've got upwelling by diapycnal mixing, which again acts to deepen the stratification. And then eddies, we'll talk about this more tomorrow, basically act to flatten the density surfaces. So they will move warm water polewards and shallow the surface layer. And what Ganadesican does is just introduces simple parameterizations of these terms, and it gives you actually an amazing set of limiting cases that correspond to different theories that have been put forward. But what you basically find is that for strong overturning and a strong ACC, because notice there's a north-south buoyancy gradient here, so this is a decent model of the ACC, you require deep stratification. And that means that because stratification is deepened by Southern Ocean winds and diapycnal mixing, those are the processes that will give you a stronger ACC, with a caveat that I'll talk about tomorrow. Actually, I don't really believe that conclusion, but if you believe in most eddy closures used in climate models, it's true. It also, as an aside, means Southern Ocean winds are important for the AMOC, and Matt, I think, touched on this. Togweiler and Samuels showed that changing Southern Ocean winds will modify the North Atlantic. So this is one coupled global problem. The Southern Ocean is just pivotal to understanding everything. And I've got a really beautiful example of that at the end of tomorrow's slides. If we have no wind and diapycnal mixing, then basically you lose your stratification. You just shallow this surface layer. And it means you get a weak overturning and a weak ACC, basically because you need thermal wind balance to give you both. And that's known as Sandstrom's theorem, at least for the overturning. But again, I'm going to put a caveat, see tomorrow, because it is a lot more subtle than that, actually, as to what's going on. Okay, how are we on time? Role of eddies. So that is the main topic tomorrow, but I want to just give a brief taster, because I think it's important. It might be useful to other talks before a talk tomorrow, and it's going to be useful for me here now. So I will go over this in a little more detail tomorrow, so this is the simplified version. So the question I want to ask is, how do we reconcile the Deacon cell with the observed water mass structures? So from the observations, it's clear that you've got two Antarctic water masses being formed Antarctic intermediate water and Antarctic bottom water, and North Atlantic deep water upwelling in between. And we saw earlier that our Deacon cell looks like this. And, well, that doesn't make a lot of sense when you look at the water mass structure. And it did puzzle people. I was a student at the time that this was the prevailing paradigm. There is more than one way of looking at what I'm going to say, but I'll give you the simple version here. So Gent and McWilliams introduced a parameterization, and their key idea, and it's a really good idea, is that fluid parcels to first order move around conserving their neutral density, whatever that neutral density is. And so they do two things. They mix along density surfaces, but that is an incomplete parameterization of eddies, because what do I get if I mix density along a density surface? It will do nothing to the density field. And so their brilliant idea, and they didn't present it this way in the original paper, it was in the 95 paper that they actually articulated this way of understanding it, is they introduced an eddy-induced velocity that very simply mimics baroclinic instability by flattening the density surfaces. So if you think about it, it's removing available potential energy. It's a sink of energy, and in Gent and McWilliams' world, that energy just goes poof. And it's one of the biggest sinks of energy, and probably the biggest in coarse resolution ocean climate models. Okay, that's all I was going to say. Now, this eddy-induced circulation is a little counterintuitive, and I remember back in the mid-90s trying to explain this to Rick Williams, saying, we need to be working on this, Rick, and I was trying to explain it on the board, and he made a very good suggestion, which is it would be really nice to come up with a tutorial example of this actually happening. So we set up a re-entrant channel, like so, and we just cool and heat to the south and the north, if we think of this as the Southern Ocean. And that maintains basically a stratification, a buoyancy gradient north-south. So it's a layered model with 3 layers. And then we just drop in a dye that goes from 1 to 0. So if you like green and yellow into these sponge layers to the south. And what you find some while later, I think it was 10 years later, is the yellow dye has invaded the upper layer, whereas layer 2 there's an equal gradient. And in layer 3, the green is starting to invade the lower layer. So the middle layer is what you'd expect if everything was just diffusive. But what you can see here is that this is not a purely diffusive process. And it's because you are actually moving water. The eddies are moving water across the basin, this eddy-induced circulation. It's not a mean flow because there's no zonal pressure gradients. So it's an eddy-driven circulation moving the dye, and hence it would move water masses across the ACC. And then the paper that really got everyone's attention was this paper in Science by Dana Basaglou et al., McWilliams and Gent. And there were many wonderful things in this paper, but in fact they fixed a whole host of known issues in ocean models at once, and we'll talk more about it tomorrow. But crucially for us today, they showed that when you included eddies in the overturning, then this Deacon cell, which dominates in the Eulerian mean, so this is the mean if you just average zonally and don't think about the eddy contribution to the transport, you have this massive Deacon cell, but when you included the eddies in this model, the Deacon cell just vanishes magically. And I don't think anyone has ever seen such an exact cancellation again, actually, but it was an impressive result and really makes a lot more sense when you think about the water mass structure. Now, I was lucky. I went on a course by Alan Plum when I was at MIT, so it would have been about 94, on atmospheric transport. And I must be honest, the main reason I went is I thought, what the nerf is Alan going to talk about for 20 lectures on atmospheric transport? Because I just thought it was all advection and diffusion. Little did I know, 30 years later, this would still be my topic of research. And And Dana Basaglou et al. Had just come out, so that had gone. But the next paper on the atmospheric list was then about what they called the diabatic circulation, and I thought, well, that must be relevant to the Southern Ocean. So I made a really simple toy model of the Southern Ocean. It's a 2D model with basically imposed wind stress, imposed pressure gradients across the bathymetry, and imposed buoyancy forcing. And what you find in this model is that the Deacon cell, of course, the Eulerian mean flow looks like this, with upwelling in the Drake Passage, a Deacon cell. But when you include the eddies, you find that the residual circulation, the sort of sum of the mean and the eddies contributions, basically is set by buoyancy forcing and aligned along the density surfaces. And I've always regretted, in the original draft, I had a North Atlantic deep water to intermediate water conversion to, and Mike McCartney persuaded me to take it out, and that was a mistake. I should have hedged my bets. So, it's a simple model, but it kind of illustrates what the meteorologists already knew in the stratosphere, but in the ocean, that the overturning circulation, and I should stress this is in equilibrium, is related to the buoyancy forcing. I wouldn't say driven by buoyancy forcing, but you can infer it from the buoyancy forcing. This paper is very well cited, but my namesake, John Marshall, published a paper 6 years later that gets all the citations. So that's a little bit annoying at times, but I even had a paper where I tried to persuade, it was Mike Meredith's review paper I was an author on, to reference 97, and Martin Fisbeck kindly pointed out to Mike the history of this, and so we managed to get the citation back. Okay, this is important. The literature on eddies in the Southern Ocean is confusing. It's often incorrect. There's a lot of double counting. I think I've seen the odd example of triple counting here. So I want to say this because you might be confused when you will be confused. It will take a long time, I think. It took me a long time to sit down and understand this stuff. So there are lots of ways of talking about eddies. So we've talked just now about eddy form stress. Eddy form stress is basically P prime, grad Z prime. And with some mathematical trickery, you can relate this to horizontal buoyancy fluxes. So that's basically what Johnson and Bryden do. So an eddy form stress is equivalent to a north-south eddy buoyancy flux. And that's weird because it means that vertical momentum transport by eddies is equivalent to horizontal transport by eddies of buoyancy. When you think about thermal wind balance, that perhaps isn't as weird as it sounds. If you change the shear by fluxing momentum vertically, you have to also flatten the density surfaces. So the two are tied to each other. And then we've also talked about this view where you get a Deacon cell that steepens isopycnals, balanced by an eddy-induced cell that opposes it. And if you get me on one of my more dynamical days, you might catch me talking about potential vorticity fluxes too, which I've kept out of these talks. So now I want to stress these are basically different ways of talking about the same thing. And there are papers that count these processes more than once, and just be aware of that. The literature is, especially the early literature, is very confused on this topic. So you need to be cautious. Okay. So where are we? 1109. So what is the Southern Ocean? So I started with this schematic. I don't know if you have any ideas, but this is my view, is that there's a kind of weird obsession with the northern tip of Drake Passage in the literature, especially in the paleo literature, actually. And I think it's often a bit misplaced. So this picture was drawn deliberately with the winds north of Drake Passage. So Dave Munday did some fun experiments as part of a paper Leslie Allison, a former PhD student of ours, wrote on where do winds drive the ACC. So the main part of the paper was something else. But what Dave did, so this is an extreme version of geoengineering. So we took a coarse resolution model, the MIT GCM. It's got a healthy 122 Sverdrup ACC. And then Dave obliterated all of the Indian and Pacific Oceans. And the transport drops to 116 Sverdrups. So winds over these basins don't do much. Mixing over those basins, if you have a large enough mixing, does do something. He then went further and obliterated the Indian Pacific sectors down to the northern tip of Drake Passage. And look, the ACC transport in this model drops to 43 Sverdrups. And that's interesting, because it's telling us that if you just have winds in in Drake Passage latitudes, then you don't get a very strong ACC. And in fact, if you look at the wind work on the ACC, most of it is north of Drake Passage. So Drake Passage is not defined only, I think, by the geometry of the basins. Maybe the other continents play a role, I don't know. But I suspect not, actually. I think the Southern Ocean itself may be a dynamic quantity. And a paper I really enjoyed writing a few years ago, it got rejected first time around because I was told nobody believes Sverdrup balance had any relevance to the ACC. And second time around, we got told off for not saying that, making that statement, because they said this was the nail in the coffin for Sverdrup balance. So you can't win. But it basically was a simple toy model. It's a reduced gravity model, so flow in an upper layer with a simplest model of stratification and rotation, basically. Reentrant channel, and we made our wind stress quite narrow because we wanted to try shifting the winds north and south. And it turns out mathematically it's pretty much identical to Gill's model, but bottom friction becomes the Gentleman-Williams eddy diffusivity. And we have stratification. So I did call it in the paper, giving Gill's model a makeover for the 21st century, because I think it's very relevant today. And one thing you can do then is shift the wind north of Drake Passage. So 500 is centered in Drake Passage, and then we shifted the wind all the way to the very north, and we narrowed the wind so we could do this. So actually the most realistic values here are this large stress of 0.4 Newton per meter squared, because when you integrate it over the forcing, it's got about the right momentum input. And so there is an effect of the latitude on the ACC transport in this model, but we're still getting 75 odd Sverdrups when the wind is at the northern edge of this basin. So I'll show you just one solution from this point here. So that's where the wind is, well north of the Southern Ocean. And look, you get something that looks quite like the ACC, but where the ACC has followed the wind north. It takes a more convoluted path to get back to Drake Passage, but it manages to do that. So I thought that was kind of fun, that, it challenges your thinking, We should redo this really with, I suspect that this model is not the easiest thing to solve because of boundary conditions, sadly, but it would be, otherwise I'd suggest it's a super problem, but it would be fun to put an Indian continent into this. I didn't mean that. You know what? Sorry, I'm having a brain freeze. You know what I mean? The other continents. One thing with teaching is once you have a brain freeze, you won't get out of it until you finish. So concluding remarks. So the Southern Ocean is a complex and fascinating region. You cannot understand ACC dynamics without a stratification, bathymetry, and eddies. The textbook paradigm is the ACC volume transport set by a combination of wind forcing, but actually, modern suspect, I believe it's wrong. I'll tell you why tomorrow. In equilibrium, the overturning cells are linked to the buoyancy forcing, and I just posed the question, is the Southern Ocean itself a dynamic entity? Is the northern boundary of the Southern Ocean really as well defined as we think? Tomorrow, what we'll do is talk about mesoscale eddy dynamics. So I'm going to go right back to basics and explain why we have eddies, what sets their scale, and so forth in the ocean in general. We'll talk about how you parameterize eddies in ocean models, and then I'll move on to talk more about my own recent work with my group on eddy saturation and rethinking ACC dynamics using our geometric parameterization of eddies. Okay, so that's it. Thank you very much.